is Rafal Studnicki. I'm a software engineer at Whatnot. And today I want to talk about our exciting journey from the days of nerve-wracking deployments, manual deployments, to the present days of seamless, continuous, automatic deployments. But before we dive into that, I'm very curious, how many of you have either used Whatnot or know what Whatnot is? A few people, cool. So for the rest of you, Whatnot is a live shopping platform and a marketplace where you can buy, sell, and engage in real time in various categories. And we're on a mission on redefining e-commerce, creating this unique blend of community and entertainment. And for example, here you can see an auction of a comic book going on. And on the first side, there's not much going on. There's just this comic book in the center of the stage. But if you take a closer look, there's some reactions. There's auction going on. Someone has win, and it looped. And eventually, the seller, we don't hear the audio, but the seller and the buyers engage via chat. And we're also one of the fastest growing startups in the US. So last year we have grown to 400 team members, 150 of which is the engineering department. And initially our deployments were very, very ad hoc, very manual. Essentially someone wanted to deploy something to production, they did it manually. But as the team has grown, that required a lot of coordination because my colleagues' changes were in main. I wanted to deploy something, and I had to coordinate. Hey, your changes are in main. I'm about to deploy code to production. Is that fine, or is there anything I need to look out for? So we improved that process a little bit, made it less manual, but still manual. So we introduced this on-call rotation, and basically every day, twice a day, in the morning and in the afternoon, a release manager went over all repositories, looked which services needed deployment, and deployed them, and monitored if there's anything going wrong with that, and reacted to that. But again, as the team has grown, our release notes started to look a little bit like this, a lot of changes in a single release. And so the burden on the context that the release manager had to have was also increased. And since the author of the changes has the most context behind the changes that are being deployed, we decided at some point to go 100% continuous deployment on all services we have. And well, merging to main meant these changes are going to production in a few minutes. And also when the release notes look closer to this and something goes wrong, it's easier to identify what the problem is if things go wrong. In this particular, that's obviously an example, but in this particular release, there are 3 changes by 3 different committers, but ideally that's one. Let me dive into high-level schematics of our system. And on the client side, we have apps on both iOS and Android, and as well as web application. And on the backend side, we have 2 main services that are client-facing. And there is a main backend crafted in Python, and there is live service written in Elixir. And if I was to describe what's the difference between these two, main backend is mostly for synchronous stuff, like you open the app, you fetch the shows recommended for you, while the live service is most really responsible for real-time and synchronous communication, like auctions, real-time auctions, bidding, chats that you have seen on that animation. And if we are to deploy this main backend Python service, that's basically stateless. Well, it has some state in the database, but here you can see 4 pods. In reality, you have more than 4 pods, but these 4 pods are independent of one another. They talk to some external services, but they don't rely on one another. And we have a user that opens the app, fetches the feed of recommended shows. This request hits one of the pods. And we utilize Kubernetes for rolling out. deployments. And it's up to the load balancer or ingress to decide which pod exactly is going to hit. And in parallel, we can start pods running new version and run some synthetic tests to verify it's working fine. And then we can tell the load balancer to switch the traffic to the new one. And in reality, what we can do and what we're doing is that we switch like 25% of the traffic first, let it run for a while, see if there are maybe some errors that we didn't catch in the synthetic test, and then go on. But as soon as we are confident that this green cluster is working fine, we can phase out the blue one. And the colors of these pods are not incidental, because this approach is called blue-green deployment. And that's the approach we unfortunately cannot use right now in our live service. And that's because the whole Elixir cluster we have is clustered. And I'll explain, I think it should be obvious in a second why we cannot do that. We technically could start the whole cluster in parallel, but with new version, but it would have to be clustered with the old version at all times. And I'll explain why in a second. But let's see how the deployment of the live service looks like. So let's say the user, a buyer, opens one of the shows. This would create a WebSocket, open a WebSocket connection to one of the live service pods. Again, which pod exactly that is, up to the load balancer, and underneath every live stream has a Phoenix channel topic. So this, when the buyer connects to this pod, they also open a Phoenix channel, subscribe to the live stream topic, and it's up to the Phoenix PubSub mechanism to broadcast all the events related to a single live stream across the cluster. And now let's say this user that connected to this pod is also a seller, and they start an auction. And when they start an auction, this will also start a process somewhere in the cluster. And in this case, we're utilizing this pattern of a single global process, which might not be the best. We might need to revisit it at some point, but currently we need it to first of all track time of the auction, and it's even more complex in our use case, because when you start an auction, you don't know when it's going to end, because bids that come in closer to the end of the auction extend that auction time. Unless these are sudden death auctions, but that's a different story. So we cannot really predict. We know what's the upper bound, but we don't know exactly when the auction is gonna end. This depends on the bids coming in, and then when the auction ends, we need to let everyone know that the auction ended and process the order. And for this, we're currently utilizing Horde library, which is eventually consistent mechanism to keep track, to ensure there's a one process running in the cluster. It's eventually consistent, it's not a consensus, so there might be a case, there might be a scenario when there will be two processes running at some point for a given auction, but they should eventually diverge. And one more thing I want to say now is that it's up to Horde to decide where the process will be started in the cluster. So that's why this process is started on the different pod than the seller is connected to. So now when we run a deployment, we start a new pod, it eventually connects to the cluster, and this pod top right, in the top right corner, has been selected to be replaced by this new pod, and it's going to be terminated. So it disconnects from the cluster, and now Horde, that also, the way it works, it supervises these processes. So it sees, okay, this process is down, it needs to restart it somewhere in the cluster, and let's say it's restarted on this pod. And this process repeats until we have the whole cluster is running the new version. So that's called rolling deployment. Again, this is just an illustration of the process. What we can do, we can as well start 4 new code pods, 4 pods with new code in the parallel, and replace them all at once. But they need to be connected to the old cluster. Otherwise, we could have a situation when 2 users view the same auction differently, the different state of the same auction. And in theory, this whole process should be completely transparent to the user. The bids should go through. The auction should end normally, even if we do the deployment. In reality, it turned out this wasn't the case. We had cases where the auction timer went down to 0, the auction never ended, or maybe the bid button was unswipeable. That's what we experienced. And this was even more common during these afternoon deployments that coincided with the higher traffic. And up to the point where we decided to pause these afternoon deployments of the live service because it was causing too much trouble for sellers. So we were in that situation. We know we're going to do continuous deployment eventually, but we cannot even run manual deployments reliably. So we had to figure that out. And we started with that hypothesis. Higher traffic, so probably more processes migrating means higher probability of this issue happening. So we took a closer look at that. We know we're not fixing the root issue. We're not trying to fix the root issue. We're just trying to minimize the number of migrations. So we looked at how the process of connecting or finding the cluster looks like. And for that, we're using libcluster and DNS strategy. I guess that will be eventually replaced with DNS query that Chris talked about yesterday. But the way it works is every 10 seconds or so, there's a DNS query issued to the Kubernetes DNS service. Pod IPs are returned, and the pods that are on the list I'm not connected to, I connect to. The pods that are not there, but I'm connected to, I have to disconnect from. And visualizing it on this diagram again, we start a new pod. It makes the DNS query. It finds these 4 pods running the old code. It connects to them. Horde might be configured. We don't have it configured this way, but can you configure that this process will be proactively moved already? Let's assume that's the case for now. So the process has moved to this new pod. At the same time, these 4 yellow pods are making this DNS query every 10 seconds as well. And the white pod wouldn't be returned in the response until it passes health checks, the readiness health check on Kubernetes. So it might take some time. I forgot what threshold we have set, but it might take a few seconds, but it was enough to discover, for the yellow pod to discover that the new pod is not there and disconnect the white pod from the cluster. And as a consequence, the process was migrated again back to this top right pod. So that increased number of migrations of this process during the rollout. So the way we sort of mitigated this problem, kind of swept this under the rug, is that we modified the strategy a little bit. We only relied on the DNS response to connect new nodes to the cluster, and we let distributed Erlang protocol to deal with disconnections. So when the pod goes down, TCP distributed protocol TCP connection goes down, Erlang will see, yes, we need to disconnect. And well, this simple change, it was a great success, actually. As I said, we just mitigated the problem. We knew the problem is still somewhere there, but the probability of issues with auctions lowered so much that we were confident enough to resume the afternoon deployments. Still not confident enough to do continuous deployments with potentially a few dozen deployments every day. So we had to dig a little bit deeper. And what we did here, so we had a few options. One option was to wait for deployments, go to live streams during deployments and try to catch it. Very time consuming. So because we already use Kubernetes, we have Docker images, we thought, okay, why don't we just try to replicate the same scenario in our tests? And that's what we did. And as a setup, we just basically make sure that we have Docker image of the current commit, basically, and the last release. So the current commit would be the release candidate, and the previous version would be the last Git tag that was created. So that's something that should be running in production right now. That can be configured by envar, but that's the default. That's how it's running in CI. And we did write a test that makes sure that users can bid during version upgrade. I know there's some detail hidden there because there's test is written using RDSL, but let me try to explain. We start with no cluster. Then we start 2 nodes, node 1 and 2, running the previous version. So that's something running currently in production. And then we connect the seller to node number 2 and create a live stream. So it should look something like this. Node number 1 is on the left-hand side, node number 2 is on the right-hand side. Then this is a little bit lower level API. The seller starts an auction. Minimum price is 10 cents. I forgot what's the auction duration seconds set to, but it's a sudden death, so the time is not going to be extended. And then we make sure it started. So here we have it. The auction process started on the first node. Then we stop the first node and replace it with the release candidate. And wait until these 2 nodes will create a cluster. So at this point, we replace the first node with the new version and expect that this auction process will migrate to node 2. And then we connect 2 buyers, one to the node number 1, second one to node number 2. They join the live. So it looks something like this. User number 1. Buyer number 1 places a bid for $1. We make sure all sellers and both buyers receive that bid. We do the reverse, the opposite thing. The second buyer connected to the old version places a bid $2. Again, we make sure both buyers and the seller receive the bid. And we let the timer run out and make sure the auction actually ended. And that's the test that replicates exactly the thing we have seen that was problematic during the rollout. And we can do the reverse thing as well. The test was testing that the users can bid during version upgrade. The reverse thing would be to switch the versions, and this way we would test that the users can still bid during the version downgrade. And this way we can get some confidence that the auction will run properly if we upgrade one version up and downgrade one version down, not necessarily if we skip one version. On that note, I completely accidentally came across this YouTube video recently where someone started with a floppy disk with Windows 1.0 and tried to upgrade until Windows 11, one version by one version, and it worked. So maybe Windows was testing, actually was testing in a similar way. So this replicates this scenario that was not working, and I said that the auction process is running on node 1, but also earlier I said that it's up to Horde to decide which node it's going to end up on. And that's true. It might as well end up here. And in this scenario, if we replace node 1 with the new version, and there's nothing interesting happening on node 1, well, there's no possibility that anything's going to break. And that was the case. When we run these tests, we've seen it's failing around 30% of the time. So it wasn't deterministically failing, but we can run it on the local machine indefinite amount of times. Still much better than trying to catch this issue in production. So we were able to run it, as I said, as many times as we wanted. We could have done logger, infos, logger, debug, whatever, tracing, and we finally boiled it down that this issue must be somewhere in the Delta CRDT code, which is the library that Horde is using to distribute the state across the cluster. And we basically wrote the same test, but on the lower level. And what this test does, we start 3 replicas, connect them into full mesh. That's our setup. Then we persist some data to replica 1. We stop replica 1, and we would expect that the value, this value will be replicated to both replicas 2 and 3. And this time, it wasn't non-deterministic. It failed 100% of the time. And to explain why that was the case, like obviously this allowed us to dig even deeper and understand what the problem was. And to explain briefly what happened, I need to very, very briefly introduce Miracle Trees. If you're into crypto, you probably know what's going on. This example is just for illustration purposes also a bit incorrect. But the idea is that, let's say we have replica on the left-hand side where we have this map ABBCC, and on the right-hand side AABB, and we want to compare them. So we start at the top level. We see that the hashes are different. This means that these data structures are different. We need to go one level down. The right subtree, one level below, is 13 on both sides. So this means this right subtree is equal on both sides. We don't need to dig deeper. On the left-hand side, it's 2 and 13, and that's why it's incorrect, because we have 2 hashes for different data that are the same. I just used like 4 bits to illustrate it, and it's easy to get a hash collision with 4 bits. But nevertheless, on the left-hand side, we see there are 2 different hashes, and we're basically already on the leaf node here. So we can directly say on the right-hand side there's just 5, on the left-hand side it's 1 and 5, so 1 is missing on the right-hand side. The exact process does not really matter. The only thing that matters here is that this process is multi-step. So there is this negotiation going on between 2 replicas. It might be the case that the right-hand side replica also has some data that the left-hand side doesn't have, and during this negotiation they need to figure out what's missing where. Again, the thing is, this process is multi-step. In reality, this tree has like 32 levels. It's also not comparing level by level, it's more multiple levels by multiple levels. But the thing was that that's where the problem was. And it was actually even directly written in the comment in the library. But we didn't know where to look until we narrowed down the problem top down until exactly this place. We basically didn't know how this thing works, right? We knew, yeah, there should be this one process running in the cluster. We don't know how it works. We don't know how this CRDT is implemented in Horde. We don't know how it replicates. We had to learn that and eventually find that line and realize that it's a known problem. And we did try to figure out how to do this properly, but we failed. So what we did here, we implemented a solution that works for us. We decided to sync the whole state at termination of this replica. We decided to send the whole state to the whole cluster and wait for the confirmation, obviously with a timeout, for confirmation that it has been accepted. It's not a generic purpose solution. It's not the proper solution. It works for us. We have it in our fork. It works for us because these auctions are kind of short, and maximum number of auctions that we have at any given time is about 300. It doesn't hurt us to send 300 key values at once. If this number was 300,000, that wouldn't work very well. We would hit some grace termination timeouts. We would have basically the same problem. But anyway, turned out this worked for us. We didn't reproduce this problem again, either with deployment tests nor on production. We haven't seen it happen again since then. So it worked for us, and it unblocked us from going 100% continuous deployment. We had to do a few more things, like optimizing the whole CI/CD pipeline process, especially fixing the flaky tests that were a little bit painful. Well, it turns out Datadog has a really nice integration for tests, not only for flaky tests, but just like summarizing what your tests are, how long they take. And for Elixir, it's actually out of the box, almost, because all you need to do is to format the test output in the JUnit format and push it to Datadog. And after fixing the flaky test, we also get a new notification right now if there is a new one. So that's pretty nice. So we were very grateful for this discovery of writing deployment tests, and later it turned out it was a great investment also. So at some time later we were running some load tests, and we've seen that there is an inefficiency somewhere. So I've shown you like a snippet of a test that's executed during an auction. We also have a feature called giveaways, where you can get stuff for free, basically, but you need to be on that stream when the winner is drawn. This is to prevent like entering a lot of giveaways and moving between shows. So we need to keep track who is on the live stream. And we found an inefficiency in that mechanism somewhere, and we realized, it turned out it's because we used Phoenix Tracker for that under the hood. Turned out the reason why it's inefficient is because we have the default pool size of 1. So I thought, okay, that's fine. That's an easy fix. We'll just change the configuration to the pool size. We set the pool size, it will be fine. Well, the deployment test said no, it's not going to work. Well, and when we've seen that output, it becomes obvious, because when you run in parallel, you run one version when there's one process, and you run a version when there are 16 processes, and process number 16 tries to sync data with process number 16 here that doesn't exist. It's never going to be replicated on the old version. So it helped us realize, yes, it's going to work. We just need a few more steps here. We had to implement like a Phoenix, like a no-op tracker that doesn't have any business logic at all. It just stores the data, just keeps track of the data, and then we added it, called v2, and when we persisted the presence data, we did a dual write. We wrote to both old and new version. When we tried to fetch something, the Phoenix get by key, the get by key had to use the old one still. We were fetching the data from the old one. When we were sure that v2 has all the data that v1 has, and it took I think a day to synchronize completely. Like all the giveaways, all the live streams had to roll over, basically. We could have make a switch, start to read from the new one, but we still had to do a dual write. Remember, we want to be able to upgrade one version up and downgrade one version down, so in case we need to roll it back, we still need to be able to go back to this v1 tracker. And after we're sure it works, we can phase out the v1 entirely. So seemingly simple change. It still was simple. It just required 3 deployments. What is after all of that experience? What is the real value behind continuous deployment? Is it just to improve the developer's experience and make sure the single deployment has a lower risk of failure? For us, one of our core principles is always listen to customers. So the main reason to do CD for us is to be able to deliver value to the users very quickly. It's not the only tool we utilize for that. We also have feature gaze, dynamic configs, experiments that when we can very quickly decide which user sees what and which user has what feature. But being able to deploy in minutes is very valuable for us. And I want to conclude this presentation with a real-world example from Whatnot, where seemingly a very, very simple change for the user can have really profound impact on the customer, on the user experience. Let's hope the audio works. It doesn't? I think it doesn't. Should that work?
Thing away from this conversation. All right. Did the winner draw? Congrats. Move the pending tab. Please. I have to use my arrow keys to get over to it. Put the pending tab right here. That's more important to me. Oh my god, you did! Oh, yo! You're a legend, dude! That is such a good change. Thank you. Did you do that for the whole app? Let's go. Can I get a W for Whatnot actually listening to everybody? They're honestly an amazing platform. I would recommend it. Buyers and sellers, always taken care of. No cap. Let's go.
So if you're interested in delivering value quickly to the users, we're hiring. There's a QR code for our job openings here. If you're not able to scan it right now, just go to whatnot.com/careers or whatnot.com and find the careers link. And with that, thanks so much for coming and for listening to our talk.